So this is the idea to represent probability with the help of area under the curve. So we are having one impulse at x equal to 1, which represents the height of impulse is not 1 by 2. The height of impulse is always infinity. So the area of impulse is 1 by 2, and area of impulse at x equal to 2 is also 1 by 2. So the second idea represents the probability with the help of area under the curve. So what I can say, there is a total area under the curve is what? 1 by 2 plus 1 by 2 is 1. So you can say fx of x equal to minus infinite to x fx of x into dx. Now what I can say, if I take x equal to infinity, then fx of x equal to infinity is given by minus infinite to infinite fx of x into dx. As we know, the value of CDF at infinity is 1. So I can say that area under the curve, the total area of a PDF function is always equivalent to 1. This is very important property. The total area of PDF function is always equivalent to 1. The total area of PDF function is always equivalent to 1. This is the idea. Now let's go for the next thing, and next thing is some important calculation or some important statistical parameters, some important calculation. Important calculations, or I should say some important calculations or what I can say, important calculations means what? Important calculations means suppose the numbers are random, and for random number you cannot characterize anything with the help of a single sample. You need average of samples. So we will talk about average, mean square value, and everything which is important in the communication system. So let's say there is one operator in communication system which is known as expectation operator. This E is known as expectation operator. This E is known as expectation operator of and this is known as random expectation of random variable x. This is also known as, this complete operation is known as expectation of random variable x. This is known as expectation of random variable. This is known as expectation of random variable x, or this is also known as mean value. This is also known as mean value. So this is first thing. This is very important because when numbers are random, we can characterize the sample, not a single thing. So you can say expectation of x is given by expectation of x, which is also known as mu x, and this is given by minus infinite to infinite x into fx of x into dx, where you know that fx of x is what PDF function and x is dummy variable. So this is the first thing. This is the value of average for a random variable x. The second important thing related to the power content of random variable x is mean square value. So let's go for the second, which is known as mean square value. Mean square value, and how you write it? Mean square value. The mean square value is power content of random variable. This is given for power content of random variable x, and mean square value is given by expectation of x square is minus infinity to infinity x square into fx of x into dx. This is known as mean square value. Mean square value. One more thing which is known as standard deviation. All these are statistical parameters. Just remember this. Not more than this is required. Standard deviation. Standard deviation, and it is given by standard deviation, and standard deviation is given by sigma x square is equivalent to expectation of x square minus expectation square of x. This is known as standard deviation of a random variable x. So it is difference of the first thing and second thing is different. The first thing is known as mean square value. The first thing is known as mean square value of random variable x, and the second one is known as square of mean value, and the difference is known as standard deviation. The sigma x is known as standard deviation. Sigma x is known as standard deviation. Sigma x is known as expectation of x square minus expectation square of x. It is the mean square value minus square of mean value will gives you the standard deviation. It's a difference from the mean. It is known as standard deviation. So these statistical parameters are very important while analyzing the random numbers. So this is our whole discussion on random variable. We will use whenever we will go for the communication system, we will use this random variable as a concept. Now, after completing this, we have the first part, which is of digital communication, known as sampling. The very important chapter, which is known as sampling. sampling. The process is known as sampling. And what do we understand by sampling? The sampling is, what do we understand by sampling? Sampling is a process of sampling is a process of converting a continuous signal into discrete signal. The process of converting one continuous signal into discrete signal, one continuous signal into the discrete signal is known as sampling. This process is known as sampling. This process is known as sampling. What is meaning of this? The continuous signal is, let's say, let me give you the easiest idea of sampling. This is, let's say, you are sampling your signal x of t, and here you are connecting this to y of t using a switch. This is one switch, and this switch is what? This switch is, let's say, on and off. So when the switch is closed, this is, let's say, y of t, or let's say this is input, this is output, and this x of t is what? Input. So what I can say, when this switch is closed, input is equivalent to output. When this is switch S, when S is closed, input is equivalent to output, and when switch is open, output is equivalent to 0. This is the idea. When switch is closed, input is equivalent to output, and when switch is open, output is equivalent to 0. Now, what is sampling? Let's say this signal is x of t. X of t is known as, because t is continuous, defined at every time instant interval, so it is known as continuous signal. Now this sampling will do what? This will convert this t into n into ts. So whenever switch is closed, first switch is closed, let's say n equal to 0. Second time switch is closed when it is ts. Third time switch is closed, it is 3ts. Fourth time switch is closed, it is 3ts. Like this. So can I say this switch is closed and open after every ts interval? So it will convert your xt into x of nts, and this x of nts is known as discrete signal. So what do we understand by sampling? Sampling is a process of converting one continuous time signal into discrete time signal. So sampling is a process of converting continuous time signal into discrete time signal. Continuous time signal to discrete time signal, or you can say this is x of t. If this is x of t, this will be x of nts. Let me give you a bit of graphical representation what we are doing. And ts is known as sampling period. Ts is known as sampling period, and 1 by Ts is known as sampling frequency. This is known as one by Ts is known as sampling frequency. So one we are having sampling period and second we are having the sampling frequency. These are two important things here. So there is a criterion for the sampling frequency. Keep this thing in mind. Now let's have a graphical representation of sampling. So we are having, let's say, some continuous signal. Continuous signals are signal which is defined at every time instant. So let's say this is my some continuous time signal. This is my continuous time signal. This is nothing but continuous time. This is known as continuous time signal. And let's say this is x of t. What is meaning of sampling? The meaning of sampling is very simple. We will go by this. Let's say you are taking first sample here. You are taking second sample here. You are taking third sample here. You are taking fourth sample here. You are taking one sample here. You are taking one sample here. Then this distance or this distance or this distance, all these distances are Ts. So let's say this is 0. If this is 0, can I say this point is what? There is this point is, this sample is x of, let's say this is Ts. This is 2 Ts. This is 3 Ts. This is 4 Ts, and so on. This is x of Ts. This sample is defined only at Ts impulse. Then what is this sample means? This sample is x of 2 Ts. Maybe Ts equal to 1. So this is x of 2. This sample is what? This sample is x of 3 Ts. This sample is what? X of 4 Ts. This sample is maybe x of minus Ts. Now your signal is defined 8 Ts or 2 Ts. It is not defined at in between. So this is lossy mapping. The sampling is a lossy thing because you are losing losing some information because this is not available now. This part of the signal is not available now. So what do we understand by discrete signal? X of nTs is discrete signal is what? Collection of samples, maybe minus of 2 Ts, x of minus Ts, x of Ts 0, and so on. The collection of samples is known as discrete signal. This is known as discrete signal. A collection of sample is known as a collection of sample is known as discrete signals. A collection of sample is known as discrete signals. Now let's go for the next part. And what next part says? The next part says that the collection. Okay, this is fine. Let's go for the next part. And what next part says? Next part says that there is a criterion for this sampling frequency. Means what you are doing, you are sampling something, but in your experience you cannot hear that sample signal if sampling is low. Means suppose you have to guess if four pillars of something is given and the only one pillar is shown to you, and they are asking the what about the whole structure. So everyone can give the different answer. This is like the sampling. The maximum sampling you can have, the maximum less lossy mapping you can have. So there is a criterion for this sampling frequency, or I should say that there is in human experience we cannot hear the discrete things. We are comfortable with the continuous things. So maybe for some purpose, for digital communication or to reduce the noise, we are converting our continuous signal into discrete signal. But again, when it will interact with the human being, you have to again convert this discrete signal into the continuous signal. That's why there is a limit for fs. That what is the idea? If the value of sampling frequency is as high as possible, means the more samples you take, the less noisy the communication will be. So what I am saying this, that there is a rule for sampling, and what that rule is? Rule for sampling. And what this rule is? The rule for sampling says that to reconstruct means what? To reconstruct means getting back. To reconstruct means what? To reconstruct means getting back your original continuous signal from discrete time signal. To reconstruct a band limited signal, this band limited is very important thing. To reconstruct a band limited signal, sampling frequency must be at least twice, or must be at least twice of sampling frequency must be at least twice of frequency of band limited signal. Frequency of band limited signal. At least twice of band limited signal. This is the idea. What it says, to reconstruct a band limited signal, the sampling frequency must be at least twice of the frequency of band limited signal. Let's say the frequency of band limited signal is FM. What do we understand by band limited signal? The idea of band limited signal is very simple. The band limited signal in which the signal lies in particular frequency band. That is band limited signal. The frequency of band limited signal is FM. And let's say the sampling frequency is Fs. Sampling frequency is Fs. Then what relationship says? Relationship there is for for reconstruction, Fs should be greater than or equal to twice of Fm. This is known as rule for sampling, or also known as Nyquist criterion, Nyquist rule. This is known as Nyquist criteria or Nyquist rule for sampling. So if you want to reconstruct a band limited signal, the sampling is not sampling don't have any restriction. The restriction is what? The restriction is because to convert a discrete signal to continuous time signal, what is needed? That sampling frequency should be greater than or equal to twice of Fm. Means if the sampling frequency is less than twice of Fm, means this is not obeying the Nyquist rule. This means a discrete signal cannot be faithfully converted into a discrete signal cannot be faithfully converted into continuous time signal. This is not satisfying the Nyquist criteria. Second one, when Fs is equivalent to twice of Fm, this is known as sampling at Nyquist rate. This is satisfying the Nyquist criteria. So this is not satisfying the Nyquist criteria, but this Fs equal to twice Fm, this sampling is known as sampling at Nyquist rate. This is known as sampling at Nyquist rate. When Fs is greater than twice of Fm, this word is known as oversampling. And when Fs is less than twice of Fm, or the same case, it is known as undersampling. This word is known as undersampling. So this is idea for the sampling. In next lecture, we will deal or we will discuss what is meaning of oversampling, what is meaning of undersampling, what is the consequences of not having, the maintaining this rate. So what exactly this is they are saying? Let's say we are having this waveform. And the signal looks like this. Let's say this is your signal x of t having frequency fm. Then what Nyquist criteria is saying? Nyquist criteria is saying at least take 2 samples in one interval. At least take 2 samples in one interval. Otherwise you are not able to reconstruct it. And if you take maximum sample, then there will be less chances of error, but less lossy mapping. But yes, at least 2 samples in one time period. At least 2 samples in one time period, and this is known as the sampling criteria, or also known as Nyquist criteria, that fs, the value of fs should be twice of fm. The value of fs should be twice of fm. What do we understand by what is value of fs greater than twice of fm? The value of fs greater than twice of fm is given by this, or the case of oversampling. And what case of oversampling says that this is good. Oversampling is always good. Let's say you are taking more than 2 samples. Let's say you are taking sample like this, 1, 2, 3, 4, 5, 6. Let's say you are taking lot of samples. So what is beauty of this? That you will have less errors. The reconstruction of this signal is simpler. Then it is known as oversampling, and this is desirable. This is needed. Next is undersampling. When let's say you are having this, and you are taking only one sample. One sample in one interval. So you cannot construct the whole message, and this is known as fs less than twice of fm, not following the Nyquist rule. Not following the Nyquist rule. This is the whole idea. Now, this is done. In next class, we will talk about a few more examples for this system. For this few examples based on the sampling criteria or Nyquist criteria, so you can understand it better. And then we will go for the pulse code modulation. The next thing of pulse code modulation, which is known as quantization. So we will talk about quantization in the next class. Thank you.